Hi everyone, this is Akanksha and welcome to my channel. As promised, this is the first video of Mechanistic Interpretability 101 playlist. Today we are going to focus on linear algebra. I'll start from the very basics and try to build a framework for you to think about the various mathematical concepts inside the topic of linear algebra. So let us begin. I am somebody who needs good reasoning to learn and get invested in anything. So, if you're like me, let us try to understand why we need to make sure that the math is mathing in our head when we are writing machine learning codes. So, consider this. Maybe you aren't an expert in math and have always been scared of math, but you must be good at something, right? Maybe you play some sport really well, maybe you cook really well, or maybe you are a great photographer. Whatever the skill you have, you likely developed it for a while. Let's say you are great at cooking. The people you see cook in real life or YouTube videos, the recipes that you follow are going to be your data, and your experiments and the adjustments that you are doing to your recipes are going to be your algorithms over the data to be good at cooking. Similarly, machine learning models learn from data and apply algorithms to get better at their tasks. Here's where math comes into the picture. The algorithms are obviously based on math because that is our computational language for everything. But get this, the data that machine learning models need are also arranged using math. So while you can certainly use libraries and frameworks to build models without deeply understanding the math behind them, learning the math provides a strong foundation that can significantly enhance your ability to work effectively and innovate within the machine learning field. So then, data, as we know, boils down to numbers in math. And when it comes to tracking the positions and orientations of different quantities of data, we have to imagine them on the Cartesian coordinate system. Do you ever wonder why this way of representation? I did, and found out that it first began with astronomers in ancient civilizations because they used grids to track movement of stars and planets, as you see here. Then came Eratosthenes, who invented a system of latitude and longitude for maps of the world, which included irregularly spaced grid lines called parallels, that is latitude, and meridians, that is longitude. And finally came a fly on the wall. So, well, the legend says Rene Descartes was watching a fly buzz around the ceiling. He wondered how he could tell someone where the fly was, and it hit him that he could describe the fly's position by measuring its distance from the walls. And voila, Descartes had invented a coordinate plane. The coordinate plane is sometimes also called as Cartesian plane in his honor. So that's why we imagine all the points on this kind of a plane. So now that we have all the fun history and origins part covered, let us explore the actual math. What does your desktop look like? Does it have any files or folders or is it empty? Doesn't matter. I guess it won't be looking like this mess. Can you imagine trying to access a file or folder from this organization? It won't be possible. And I don't think any system today allows us to organize it in this fashion. We have these imaginary grid lines that we have to strictly follow, and we can only arrange the folders in this fashion. So consider all of these data points, and these data points are going to be the vectors. And the strict way to arrange them in these grid lines is basically similar to vectors being arranged in matrices. That's what vectors do. Each data point becomes a vector, a straight line pointing from the origin to its place in the space. What if you have a whole swarm of these vectors? You take all of those neat little lines and put them together in a matrix. Think of this matrix like a grid, a very organized table of numbers, each one sitting on its little cell. This grid is so powerful because it lets you handle and manipulate huge amounts of data all at once. It's like having a super efficient filing system for all of your data. Efficient representation, clear organization, and easy processing. That's the beauty of linear algebra. Now let us see what vector space is. The name itself indicates it being some sort of a vector club, where all of them follow the rules, right? This is exactly what it is. Think of a vector space as a collection of vectors that can be added together and multiplied by scalars while satisfying certain properties. let's look at one, for example. If you have vector u and vector v, which is a part of vector space capital V, then it says that the addition of vector u and v should also be in the vector space capital V. And similarly, you can take a look at other properties as well. Now, after vector spaces, let's look at the concept of span of vectors. As you can see in this image, it's basically a set of all the linear combinations of a number of vectors. And understanding the span helps us know what parts of the space we can reach with our vectors, which is very crucial for solving linear equations, optimizing systems, and even for understanding the capabilities of machine learning models. So for understanding linear transformations, let us make a sourdough bread. By that I mean, think of the process of kneading the dough. You might be aware that we perform a lot of actions on it, like squishing the dough, stretching the dough, and folding, as it helps develop the gluten network, which gives the bread its structure and its elasticity. And all these actions make sure that the yeast and the ingredients get distributed equally, ensuring a uniform texture and flavor throughout the bread. Each of these actions is a transformation. Now consider this. If every line on that piece of dough stays straight and the parallel lines remain parallel, you've got yourself a linear transformation. As one of my most favorite YouTube channels, 3 Blue 1 Brown says, transformation is just a fancy word for functions. And it is apt because it makes us think of movements like you can see here. We can take an input vector and apply some transformations to it to get an output vector. So here is something that we can remember. These linear transformations, whenever applied, can be visualized as squishing or stretching or morphing of the space where the origin remains fixed. The key takeaway here is that linear transformations can be completely determined by where they take the basis vectors. This is because any other vector could be described as a linear combination of these basis vectors. So let us understand the concept of matrix multiplication as composition. I've taken some screenshots from the 3 Blue 1 Brown video over the same topic. I highly recommend watching all of those videos to visualize all these concepts. So let us look at this vector, the one in the yellow arrow over here. What we are doing here is applying a rotation transformation to it. So basically we rotated this vector 90-degree counterclockwise. And here we are applying a shear transformation. So the new linear transformation can be called as the composition of two separate transformations, rotation and shear. If you were to take a vector and pump it through a rotation and then shear, the long way to compute the result is by first multiplying the vector by rotation matrix and then multiplying the result by shear matrix. This is numerically speaking same as applying a rotation and then a shear to a given vector. So no matter what vector you choose, the result will be same as multiplying the vector by this composition vector. Since this new composition matrix is supposed to capture the same overall effect as a rotation, then the shear action. There's this nice paint analogy that I found on a blog by Mike Penetian on concept of basis. Suppose you're a painter on a very tight budget and you need to buy some paint, but you are not exactly sure what color to get. So if you're smart, you'll buy just 5 colors: red, yellow, blue, white, and black. Sure, green would be nice and pink would be cool too. But you don't need to buy pink and green paint because you can combine red and white paint to make pink and yellow and blue to make green. Red, yellow, blue, white, and black are the minimum set of colors that you need to make any other color. We could say that these 5 colors form the basis for the whole color spectrum. We call the concept of span, which is a set of all linear combinations of a number of vectors. So since you can make all of the other colors blending these 5 colors, we could say that these 5 colors span the set of all colors. And each color in the set of 5 is necessary because it cannot be made by any other combination of the leftover 4 colors. So we say that these 5 colors are linearly independent. Remember these two properties because they define basis. Take the vectors 0, 1 and 1, 0 for example. They are linearly independent because there is no way to scale the vector 0, 1 into the vector 1, 0. Additionally, these two vectors span the entire 2D space because you can rewrite any point in this space as a linear combination of this 0, 1 vector and 1, 0 vector. But it's the same case with these two vectors 1, 1 and 1, minus 1. They are also linearly independent. And from all the pink linear combinations, it is clear that they also span the entire 2D space. This is one spot where vector spaces are different from the paint analogy. With paint colors, we really only have the basis of yellow, blue, red, black, and white colors. But in the world of vector spaces, any space has an infinite number of bases to choose from. In general, a basis is the smallest set of vectors possible that can span a space. Now let us understand the concept of rank, looking at this example. If we know that 2 apples and 3 bananas cost $7 and 3 apples and 3 bananas cost $9, then we can figure out that the extra apple must cost $2, and so the bananas cost $1 each. Remember that there are two variables here, which helps us decode the information. Hence, the rank here is 2. But consider this. If we know that 2 apples and 3 bananas cost $7 and 4 apples and 6 bananas cost $14, we can't go any further because the second row of data is just twice the first row and gives us no new information. And this is why we say that there are two variables here, but the rank is only 1. So basically, the rank represents the maximum number of linearly independent rows or columns in the matrix. Consider this example here. To find the rank of A, we need to determine the maximum number of linearly independent rows or columns. One way to do this is by transforming the matrix into its row echelon form using Gaussian elimination. This means we perform row operations until the matrix looks like a staircase of zeros. So here we have the matrix in row echelon form. To determine the rank, we count the number of non-zero rows. In this case, there are 2 non-zero rows. Therefore, the rank of the matrix is 2. But what does this mean? It tells us that the original set of rows or columns in our matrix spans a 2-dimensional subspace of the 3-dimensional space. In other words, only 2 of the rows or columns contain unique or non-redundant information. To further verify, we can check if the columns are linearly independent. The rank of the column space will also be the same because rank is a fundamental property of the matrix. Another important property of matrix is the trace. It is defined as the sum of all the diagonal elements in the square matrix. To calculate it, you simply add up all the elements on the main diagonal from top left to bottom right. It is only defined for square matrices, where the number of rows equals the number of columns. The trace is always linear, meaning that the trace of the sum of two matrices is equal to the sum of their traces. And scaling a matrix by a constant scales the trace by the same constant. Another important property is that the trace is invariant under similarity transformations. In simpler terms, this means that even if you change the basis of the matrix, the trace remains the same. And now we come to the determinant of the matrix. As you can see from this equation here, it is a scalar value that can be computed from the elements of a square matrix. It provides important information about the matrix, such as whether it is invertible and how it scales volume in transformations. The determinant has several key properties. Firstly, the matrix is invertible or non-singular, if and only if its determinant is non-zero. This makes the determinant a quick way to determine if a system of linear equations has a unique solution. Another important property is that the determinant of a product of matrices is a product of their determinants, which simplifies many calculations in linear algebra. As you can see, the factor by which a linear transformation changes any area is called the determinant of the transformation. So, if the determinant of matrix A is 6, then it means that the transformation is 6 times the original area. If the determinant is 0.5, then it means that the area will be half. And if the determinant is 0, the area collapses to zero, meaning that the transformation squashes the plane into a line or a point. And now let's understand transpose. As you can make out from this image, it is basically swapping the rows and the columns of the matrix. Given the matrix A, its transpose is denoted as this. So the first row of A becomes the first column of A transpose, and so on. Transposes are critical in defining symmetric matrices, where a matrix equals its own transpose, and orthogonal matrices, where the transpose is equal to the inverse. In data science and machine learning, transposes are often used to adjust the orientation of data, making it easier to apply certain operations or algorithms. Now, this is a fun example to understand the change of basis. Imagine an alien civilization with mathematics similar to ours, but using a different version of the coordinate system. Suppose they are visiting Earth, and we have agreed to meet them at a specific point in space to greet them for the first time. To ensure that we arrive at the exact same location, we must have our coordinate systems coordinate with their coordinates. A little bit of inception going on there. But yeah, so this is where the concept of basis transformations comes in. And a point in our Earth coordinate system is denoted as this. Now look at the alien coordinate system. Consider these are the basis vectors for them. And this is how the alien point is described. So to meet at the same location, we need to transform our description of the point from their basis to ours and vice versa. This process is called basis transformation. It basically involves converting the coordinates from one basis to another to ensure both parties are speaking the same language in terms of location. So to convert their coordinates ABC to our system XYZ, we need to express each of their basis vectors in terms of our basis vectors. Suppose their basis vectors are described this way in our system. So then the transformation matrix B converts the coordinates from their system to ours using this. And to convert any point from the alien system to ours, we multiply the alien coordinates by the inverse of this matrix B. And by converting the coordinates using the basis transformation like this, both humans and aliens can describe the meeting point accurately in their respective systems. This is how basis transformation is applied. And now let us understand the concept of eigenvectors and eigenvalues. Consider this plot here. It is basically applying a shear transformation to this letter f. Most vectors are going to get knocked off their span during the transformations. As you can see, some special vectors do remain on their own span, just as the one here, which is aligned with the x-axis. Meaning, the effect that the transformation has on such a vector is just to stretch it or squish it like a scalar. Meaning, the transformation matrix here has no other impact on the vector apart from just stretching or squishing it like a scalar. So these special vectors that don't get knocked off their span are called eigenvectors, and the values with which they get stretched or squished are called the eigenvalues. As you can imagine, the eigenvectors give us the axis of rotation in case of 3D vectors. And eigenvalues, which are imaginary numbers, generally correspond to some kind of a rotation in the transformation. You might be wondering what's the importance of eigenvectors and eigenvalues. So let's go back to basis transformations. Can you imagine calculating 100th power of a matrix? It's going to be very difficult, right? But instead, if you transform the basis vectors to eigenbases, then it becomes a very easy computation. Why? Because the eigenbases are matrices with identity matrix holding eigenvalues for eigenvectors. So the calculation obviously becomes very easy. So that's the end of our first episode of the Mechanistic Interpretability 101 playlist, where we covered data representation, vectors in matrices, vector spaces, the concept of span, rank, trace, transpose of matrices, determinants of matrices, change of basis, and eigenvectors and eigenvalues. I hope through this video you got a brief overview about all the different concepts in the linear algebra space, and now you will be able to imagine or visualize all these different operations whenever you code them while developing your machine learning models or while playing with the data. I would highly recommend to watch the 3 Blue 1 Brown videos as they are really helpful in grasping all of these concepts in more detail. And bonus points for exploring all of these concepts more in detail by solving the math by hand. That is definitely going to make your understanding more concrete. So I'll see you in the next episode of this playlist where we will be diving into some more basic concepts in the space of machine learning. Cheers!